summarize it in one sentence. It's been a lot of fun. I appreciate all the opportunity I was given at NRL. I don't know what it would have been like going to university, which I'd hoped I would do when I got my PhD. But I have to say that it's been a great opportunity, and it goes very fast. And I hope that all of you have had as much fun in your research careers as I have. By way of outline, I was trained as a superconducting physicist at Indiana University. I was born again as a surface analyst, and I spent from '76 to 2011 at NRL. I have also become a tribologist by applying the surface analysis that I had learned as a postdoc and then in my first few years to problems of friction and wear. As was pointed out, I spent a lot of time thinking about third bodies and friction, and that paid off even though they're pretty messy. And as you also heard, I spent a lot of time doing in situ methods, not only in tribology but also in other related fields. This seeing is believing approach for me was both fun and informative, and as I said, it went on, as you heard, to studies of barnacle adhesion and also on lubrication of armatures and railguns. And then I'm going to talk a little about what I've been doing in the last year since I retired. This is almost the same, but I want to point out what it takes to get through 35 years. It was very exciting doing new science, and I did that for a year and a half before I was hired. Finally, a real job, which my wife never believed I'd ever get. My first sanity check, because work can be awfully hard when you have administrative stuff, is I had the opportunity to go to the Instituto de Fisica in Mexico, and it was very nice because my wife Joan had just been hired to play in the orchestra down there. In '83, I was asked to take over the tribology section, which I did. Then by '85, I was ready for another sanity check, and I had an opportunity to go to Cambridge University, where at the time the David Tabor lab was probably the most famous. David had just gone into retirement, but I got to meet many of the players from his group, Ken Johnson and a number of others, Jim Greenwood, and a lot of other scientists. I took the opportunity there for the first time in my career to really learn material science. So much of my time was spent taking courses, sitting in the undergraduate classes in what they call metallurgy, material science, and eventually that paid off as I did get some very good schooling in thermodynamics. The next major milestone was when Hubert Pollack visited me on sabbatical. He and I had a chance to talk about, he was moving into micro contacts, I was still doing macro. We had Uzi Landman come up and he was telling us about his simulations. Rich Colton was doing atomic scale measurements. And what we realized is the people who were making the big headway in the atomic scale had no idea how much of the literature, how much was understood on the macro scale. And we thought by bringing these new Turks, so to speak, in together with the people who'd been prominent in developing the macro tribology, we could accelerate information, and that turned out to be true. Sanity check number 3, I had an opportunity while I was at Cambridge to visit European tribology labs, and I became very impressed with the kind of work that Jean-Marie Georges was doing in Lyon in the various groups that his students had built up. So I took advantage of what I had learned here, made some contacts, and did some research here. And then I had an opportunity to work on some equipment, in fact, UV surface analytical tribometer, which quite a few of you know about, which was a very exciting opportunity and very profitable. Time went by very fast. It was Kathy's turn by December 2008. Kathy came as a postdoc to work with me right about the time I went on sabbatical, and she took over the group, and finally enough was enough. I retired in September 2012. Now, as a PhD student in physics, I had to spend a lot of time thinking about processes which you couldn't see. A lot of my work was in modeling, a lot of computational mathematics of electron density of states, phonon density of states, interactions, and that was very difficult in many ways. It wasn't easy to see it, but I also spent a lot of time having to make equipment, electronics, and especially thin film junctions that would actually behave like superconductive tunneling materials. And that really brought up an interesting question. How do you begin if you're a person who's into seeing is believing? How do you understand what's going on? It wasn't difficult to understand how electrons form phonons, but I could never understand how is it possible to make these actual films in nature. The questions of chemistry were a mystery to me. When I first made the junctions in the summertime, I had to glow discharge the films to make oxides, to make tunneling barriers, otherwise they were leaky. In the winter that didn't work, but in the winter I discovered you breathe on them, you can get a very nice junction. It was all magic to me. So I came to the chemistry division at NRL doing some tunneling work, but I wanted to learn chemistry. And over the next 30 years, I learned enough material science that I could fake it in lots of areas. My first lesson in chemistry...
You can be proud of the many new sources, the uses, and the exciting chemistry which have resulted from this program.
Chemistry after that wasn't so bad after all. But I had to learn analysis, and I had no experience, so I needed some...
Now, some oxide films have got some fantastic features on them. Why don't you take a look here?
As seen in the SEM micrograph, the oxide scale exhibits a dimpled but smooth texture. However, below the oxide layer, a columnar structure supports a network of cells containing dendrites, crystallites, and neophytes.
With that kind of tutoring, I had no trouble becoming a surface analyst. And it was a lot of fun. I got to learn how to read the periodic chart and all kinds of things that physicists generally don't learn how to do. I really became wrapped up in the surface analysis. I really didn't, however, understand tribology.
Oh, hi Al. I'll be with you for the loop job in a minute. I gotta finish Coffee's car and then Sawfield's car.
The secret I discovered to becoming a tribologist was just get in there and do things, even if it meant lifting the hood of your car and getting out the wrenches. My first program was ion implantation.
Ready? Aim. Ah! Need higher flows.
It's amazing how much you can learn about implantation. By that time, I was ready for a sabbatical. Fortunately, I had an opportunity to go to the Instituto de Fisica in Mexico City, a lovely new campus. Had a chance to work on some very sophisticated equipment. They had purchased a very nice UHV chamber with OJ, XPS, and leads, and we hooked it up to an RBS system. And we were able to examine the oxidation in situ with both the XPS and surface analytical techniques and RBS to watch the processes of segregation and oxidation below the surface. I also had a chance, since they weren't very efficient in getting work done, to visit many of the marketplaces, and this is my wife, my daughter, and my son. My wife's sitting here. And I had a chance to explain to them what I was doing. I explained about OJ analysis of well-ordered lattices, so they became very skilled in the kinds of surface analysis I was doing. Then I went on to work with John Mintmeyer.
Carter and I have been working on a new SDI proposal. We've been using the computer facilities here at the chemistry division and over at Cray to simulate some of our future defense capabilities.
I tell you, those were really heady times back in the 80s. Well, ultimately I began to investigate friction films, the messy world, and I did that because there was so much to be learned and no one knew very much about it, but nobody believed what we said about it, so we had to get into this new mode, believing is seeing. You had to be able to see what's going on to believe it. And this you know about. This was probably the ultimate in our opportunities to tell people what was going on in sliding contacts, what was going on both physically as well as chemically by combining optical spectroscopy with the optical microscopy with Raman spectroscopy while we're getting hard friction measurements. And you've heard a lot about the results from Tom and others. And this is an example of what we showed that we were able to do, getting chemistry while we're seeing third bodies forming. And as you've heard, one of the things that I was able to then do is say, well, if we can see what's going on in sliding contacts, let's apply the problem to the easy release. And this is the example that Kathy showed, using pseudo barnacles, force rings with transparent adhesives and coatings. What was interesting is I had done this work. It took a while to convince the chemistry community working on these easy release coatings that that was really going on. The experiments in the lab done at essentially millimeters or sub-millimeter per second pooling were interesting, but they wanted to know if that had anything whatsoever to do with barnacles coming off the side of the boat. So I worked with Jeff Swain and his students down in Florida, and we set up a rig. We put together test specimens of pseudo barnacles, as they're called, different shapes and lengths and sizes of, they were really painted wooden blocks and cones. And we had panels made, and we were going to go out on a boat and test them with a high-speed video camera. They had a little bottom of the boat had a platform with a transparent layer. We were able to go and to see the release between 5 and 30 knots. So we got all set up to do that. Everything was all set. This is what we intended to film. Unfortunately, the boat wasn't ship shape. It had sunk the week before. But I had done all this preparation, spent a lot of time making all of these pseudo barnacles, so wanting to get some result from this, we decided there's only one way to get high-speed flowing water, and that was call out the fire department. Useful. We're actually able to show that even though we weren't in a boat, just a high-speed water impact did release the barnacles in the order we predicted. I also used the same approach to study the railgun. In this case, it's a subsonic railgun. For 3 years, they were attempting to fire copper-based armatures inside a copper railgun, and they were wearing out the rails, and it was a real mess. And I wanted to find out why, but I also wanted to apply some of the tribology I'd learned, especially on how simple thin films can affect both friction and wear properties. And this is my first contact actually with electrical properties. This is a picture of the armature we used. It was Delrin. We had copper staples, and here all we're doing is rubbing with a piece of Rulon, which is a reinforced, fiberglass reinforced Teflon, simply rubbing onto this surface. A lot of surface analysis is done later. Basically, something as simple as this can put a monolayer of Teflon on the surface, and you see it makes a major difference. So we did that. We also inserted the same Rulon on the armature so it could re-lubricate the rails every time down. And one of the things that always happens is loading the bullet into the breech, and this is the all copper. In. And with a lot of finesse and belly, pushes it in. And probably one of the things that I've enjoyed most about science is you just get in the lab and get it done. Forget about designing the best, most efficient way to do it. Forget about the spec. Just get it done and show it can be done. And that's what we did in this. And a lot of this work was done by hand or belly. And here's an example. Here we're looking down the breech. And this is what a typical copper staple armature looked like. We get extensive amount of sparking. With the Rulon, we reduce the sparking to next to nothing. So we showed by just putting down a very simple layer, we could change both the friction and wear properties. To mention, this would last maybe 5 shots. We had no trouble getting 100 shots with this simple rubbing of Rulon on the contacts. So where did the time go? Transition was painless. I learned that friction and wear behaviors weren't simple, but they could be understood. First, you had to ignore the wisdom of the marketplace. Applying as much surface analysis as you can makes a big difference. You can always learn something new with the next technique. Spend time looking at the things that other people find too complicated. There's always room. And develop in situ methods for understanding behaviors, seeing what's going on. 35 years went by very, very fast. Then I retired. But I was able to combine my love of travel, mountains, streams, and valleys, with my addiction to science. I started to take geology courses. And if you want to think of it as a tribologist, the Earth's surface is the biggest wear scar you'll ever get a chance to examine. And as they say about history, someone once said about history, history is stuff and more damn stuff going on. The same is true of what you learn about how the Earth was formed and how mountains and valleys were formed. It's always going on. It's a very complicated process. But by learning the geology, I get a feel that I understand something about what makes Earth as beautiful as it is. I'm going to tell you about 2 very interesting. This is a rather simple process compared to, for example, how, the Appalachians were formed and wore down. This is going to tell you about 2 plate tectonic events. One from the deepest part of the Earth, the Marianas Trench, and the other on the San Andreas Fault. Fairly relevant, the latter one. The Marianas Trench. As some of you might know, many of you from just reading the news in the past 6 months, that someone, what's his name, Cameron, just went down there. It's the deepest valley on the ocean floor. The trench was created by subducting plates, the Philippine again.
Subduction occurs where 2 tectonic plates collide. As they grind past each other, the heavier plate is pushed beneath the lighter plate. the descending plate is forced down into the Earth's intensely hot interior called the mantle. It takes with it water and sediment built up over millions of years. As the descending plate dives down, it digs into the mantle. Here, the colliding plates form a trench, a giant crease in the ocean floor.
Normally, subducting plates will produce earthquakes, like the Japanese earthquake. But no earthquake occurs along the Marianas Islands, which is very unusual. And I'm going to give you a little of the geochemistry behind that. Why, if that kind of grinding creates earthquakes in most places, doesn't it happen here?
But the Marianas Trench, the deepest subduction zone in the world, hasn't caused a devastating earthquake since records began in the 17th century. Investigators needed to know why. They hoped the trench's shallower western edge might provide the answer. Here they found an intriguing chain of underwater hills 2 miles below the surface of the sea. Engineers drilled down into the hills and collected core samples. The fine powdery mud is made up of a soft type of rock that has been ground up in the subduction zone.
An unusual kind of mud in the Marianas is made out of serpentine, and serpentine is a very weak rock, and it can be scratched with a knife or something like that.
Investigators realized the grinding plates crush the soft rock to form a lubricating mud that prevents large earthquakes.
Well, that's not an isolated case. As you'll see, a very similar tribological process is taking place on the San Andreas Fault. So here, the place, again by doing chemical analysis, they discovered very low friction rocks, and they associate that with creeping instead of quake-type stick-slip events. How about the San Andreas Fault?
The San Andreas Fault is one of the most dangerous geological features on Earth. Since records began, there have been 13 large earthquakes along the San Andreas Fault.
The water lines have ruptured. There is no water coming out of the fire.
Before the earthquake, it was a solid boundary fence dividing 2 fields. But when he recreated what had happened, Lawson realized that the land had jolted apart and torn the fence in 2.
That's what's typical about the motion of the San Andreas Fault. But there's an exception.
The small town of Hollister is unique along the San Andreas Fault system. It's never had an earthquake, plenty of clues suggesting that the land must be moving here, and walls that are bent out of shape. But then, the investigation moved 100 miles south to another small community where the land also creeps along. The movement here around the bridge is strikingly similar to the slow creeping ground of Hollister.
And you know, the San Andreas comes off the flank of that hill and right across that field, right under the bridge, and then right over by the corner of that building, or that fence post, and then on off to Middle Mountain.
What we're looking at here are cores from the active San Andreas Fault from a depth of about 2 miles. So for the earth science community, these are like moon rocks.
Buried within the rock cores, they found a vital clue about the way that land slips along the San Andreas. They found serpentinite.
The reason that serpentinite is so interesting is that serpentinite is very easily altered to talc. It allows the rock to slide at very low force levels. Talcum powder is very slippery.
Talc's crystalline structure of soft, sliding, flat plates makes it one of the slipperiest rocks known to science.
In Central California, we see that the secret of the slipping San Andreas Fault is actually the rocks themselves.
For those of you who can't quite grasp something as large as core samples and analysis, think of fib analysis of surfaces in TEM and you'll get the picture. All right, just to give you a background, serpentinite is a rock that's composed of one or more serpentine group materials. These materials have this composition, and there are various reactions by which serpentine minerals can become talc. There's a whole class of these materials that are known to be very slippery. There's a lot of triboscience that is now being done on these. People have gotten fault samples from that episode that you saw there. I think that was taken back in 2005. A lot of work has been done to identify the materials involved. Geochemists do this. There's been quite a bit of tribology done on that. The kinds of studies in the temperature range at which the faults may be moving. Work by Terry Tullis's group, who many of you know, showing that if you move at a certain speed, you get something that he calls flash weakening, where the friction drops. And these are the speeds at which faults are expected to be moving very slowly, of course. One of the interesting things, and this got me thinking about it, is reading a paper where they simply put the material in and they find that they've got to have at least 50% of the minerals to get the low friction. And I'm thinking, you know, this is a problem we always deal with. Do you really need the bulk material to get the low friction, or could we be dealing with the third body problem? And so these are the kinds of questions that I would ask the geochemists. If indeed there is some kind of third body forming, you may not need 50%. You may, during the sliding process, bring the more slippery material, which is being converted here in the fault, to the surface. So you may not need 50%. That's because that's not recognizing the third body issue. I would also think that the techniques that we've been talking about here, in situ sliding and using Raman spectroscopy, it wouldn't be too hard to build a chamber in which one could do in situ analysis, watching what's going on with these minerals, having the Raman there, and discovering what's going on at the interface, whether tribochemical films are being formed. And I just did some literature research, and it turns out that most of the exciting spectra, most of the materials that you get Raman spectra from, are indeed minerals. These minerals are quite complex, and there's a lot of Raman spectroscopy. So I could see that as a nice approach. All right, so what are my future plans? On Wednesday, my wife and I are going out for a week, and I look forward to taking a trip up the coastline with my new favorite friend, which is called the Roadside Geology, to northern and central California. Anyway, it's been a real trip being a tribologist. I feel like I'm still doing it, and I hope that you all have as fun a career in science as I did. Thank you.